first question I'll start with is, let's try to come up with rational numbers that are close to pi. And so if we're coming up with a rational number close to pi, we need to say what we mean by getting the rational numbers that are close to pi. What's the first number that you might say is close to pi?
3.
3. Sure. I mean, because pi is like 3.14. So if we're going to approximate pi, erase this and approximate pi. Now you might get 3. What's another approximation that you can get that might be better?
22 over 7.
22 over 7. That's interesting. Why 22 over 7 instead of 31 over 10?
Because 22 over 7 keeps going.
But that, I mean, does that make it better versus 31 over 10? I mean, this is 3.1. We're looking for the best approximations. We can get 22 over 7. We can do a little bit of arithmetic over here. 22 divided by 7 equals 3.1429. Actually, I'm not getting enough digits here. It's a rational number, 3.1429. To some extent, if I was working base 7, this would be 3 and quote 0.1, where it would be 1/7. And the fact that this happens to be an infinitely repeating decimal is something to do with the fact that we're in base 10. But if you look at pi, what is pi approximately? You should be able to say a few digits of pi.
3.14.
3.1415. It keeps going something like that. This one is definitely closer to this than 3.1 is. So it's definitely a better approximation. And it's a better approximation with a smaller denominator. And so I think that makes this definitely a better approximation. But the question is why? If this is a better one, if you were going to find the next approximation after this, what would the next one be?
I don't know what it is, but I know there's some Chinese approximation. It's closer.
Would you go like, go add more digits in numerator and denominator?
Well, I mean, here we could go 31429 divided by 10,000. Is that necessarily the right algorithm to do? I mean, it didn't seem to work so well here. And so here's a nice trick that's going to get you a good approximation of this, and is going to be what we mean by a good approximation. Instead of saying best rational approximation, which is hard because there's infinitely many rationals and they can all get very, very close, it's pretty clear if we say what's the best integer approximation. Maybe if you want to be really precise, we can say let's find the greatest integer less than or equal to. If we find the greatest integer less than or equal to, this is certainly greatest integer less than or equal to. Well, as soon as you can do that, what you realize is that works really well if you've got a number that's 1 or more, right? I mean, if you have 10.483, you pick 10, and then it's got some small remainder. And so when you're looking at the pi, you've got the 3 part, and then you've got the remainder that's the 0.1415, etc. So the question is, what do you do with the 0.1415? And in mathematics, like Zvezda was doing this the other day, she said, if you figure out a way to do something, if you can repeat that process or put it back in that framework, you can do it again. And so I'm writing this as 3 plus some remainder, and this remainder is between 1 and 0. If I have an x that's bigger than 1, and we're looking at irrational numbers, then I can take the greatest integer part of x as a good approximation. I want to combine these sort of 2 steps, so I'm going to get an x plus some remainder. Well, if I want to use this thing, if I have a number between 0 and 1, do you know how to make a number bigger than 1 out of it? and this should be special to rational numbers, and so what can you do with rational numbers?
Multiple 100 or, well, no.
Well, I mean, I don't know if my number is 1/1000th and I multiply by 100, I'm still not
Yeah,
bigger
yeah.
than 1.
Oh, that's
So what's special about rational numbers? What can you do with rational numbers?
Inverted.
You can invert it. If you take a number, if you've got a rational number and it's less than 1, it means it kind of looks like a fraction, like 17 over 253. The number on the bottom is bigger. If you invert it, suddenly the bigger number's on top and it's bigger than 1. So we could take this, if we want to figure out what's happening to this remainder, I could take this 0.1415 and I could flip it and get a 1 over 0.1415. And so this is going to be 1 over our remainder, which I happen to have a calculator here. I can go 1 divided by 0.1415, 7.061. This thing is approximately 7 point some other remainder, right? So this is 7 plus remainder number 2, which means that if I want to approximate this thing, if 1 over the remainder is 7, the remainder should be 1/7, and that's how I get 3 plus 1/7, which is exactly this guy. If we want to go the next way up, let's do this a little bit more systematically. I'm going to have pi equals an x1 plus an r1. This is a 3 plus. And then when I want to look at the r1, I'll write r1 equals pi minus 3, 1 over r1, I might call that an x2, equals 1 over pi, then 1 over r1 is 1 over pi minus 3, which is maybe an x2 plus an r2. This was a 7, and now I can figure out what that r2 is. To figure out what that r2 is, we can just do this formula here with the computer. We're going to take pi, this 3, and we'll take 1 over that. That's how we got our 7 again, I'm reiterating. Now, to get the next piece of that, we're going to take off the 7, and so I'll go minus 7. That gives us a remainder, and what do we do with that remainder if we want to get a better approximation? So when you have a number that's between 0 and 1, which is what a remainder, we flip it. So we go 1 divided by that thing, and we...
This assumes you already know what pi is, I mean, when we're putting this in the
Ah,
calculator.
so there has to be some way to compute pi or estimate pi.
Right.
You only need to be able to estimate pi, which we can talk about that. So here we're getting the 15.9. So this is 15 in some remainder, which will tell you what the next estimate means, because that means that the 7th is really 7 plus 1 over 15. And so that means that the next approximation should be 3 plus 1 over 7 plus 1 over 15, and we can keep going like this. This type of expression for a number is called the continued fraction decomposition. Exercise maybe is simplify that compound fraction and you'll get the next best rational approximation to pi. I in fact have a handout about continued fraction decompositions that I can give you that has some questions. One of the questions asks about what this has to do with a business card, which maybe I'll say and answer it over lunch. But what does it have to do with music is maybe more to it. And so let's take a look at one of the things that we had and where our problem with Pythagoras arose. I'll turn this away to maybe give us a better view. So we saw here that whenever you had a tone, you could keep multiplying and keep multiplying, and then if you got two tones that were too close together, it became dissonant and it didn't sound very nice. All right? So, we have this scale. We've got the 1, we've got the 2, we've got the 4 and the 8, and then we're going to subdivide it somewhere because we want to have more than just octaves. We want to have some tones in between. And if we subdivide it somewhere, let's just for a second call this X, then I should also be able to, what would another element that I should be able to get be? So like when we had the fifth, I could start out with nu naught, and I could go to nu naught, and I could go up 1/5, and that should sound nice. That should be in our scale. And then we were able to
Double.
go up again, right? I should be able to do a fifth on top of a fifth. So that means that I should be able to take 1 times nu naught, x times nu naught. So if I have an x times nu naught, then I would also have so what other notes would I have? So what is it that I'm allowed to do? As soon as I have an x times a frequency, I also have, what is this?
I mean, that frequency to a power.
So that would give me x squared times my nu naught,
Oh, okay.
right? And it would give me x cubed
Cubed,
times that
okay.
frequency, and x to the 4.
So you're saying
et
it's a
cetera.
geometric.
It's a geometric progression. We saw that with the 1, 2, 4, 8, which was one good unit to divide things in, but now we're trying to divide it into some other unit and figure out what that other unit should be. And certainly one of the things that we want to have happen here is, do we want our x's to go up and never line up with these octaves again? What happens if they do that and they don't match up? You'll get points where they're close but not exactly right. In other words, you'll get things like that syntonic coma, which we didn't like. And so that means that you want x to some power to equal 2. And it should be some rational power, or it could be 2. So I certainly want x to the n power to equal 2 to the m power when I look at x. So that means I go up so many octaves when I go up here. Rearranging this means x should equal 2 to the m over n. I'm doing a little bit of algebra. I think you can explain this to your students. So this is one thing we want. We want this. So it's steps turn into octaves. That's one thing that we want. The other thing that we want is we'd like to have some nice tone. Well, what's the next tone that you pick up after you pick up the 2, 4, 8? What was the next one we picked up?
You mean the 1/3 and the 2/3?
Which when I do it in the frequency domain instead of 1/3, 1/3 was the wavelength domain. When you
Right.
do it in the frequency domain, the 1/3 turns into
The 5/4.
5/4.
Oh, right, 5.
the 5/4 is, so unfortunately there's two uses of the word third here. Here I mean third in the frequency, not
mean
the
3
musical
over
third.
2.
And so here I mean 3 over 2.
Because you want to keep
Sure,
it between
which
1
we could
and
just
2.
make it even 3 if we change it by an octave. In other words, I would like to be able to take some number of steps. It doesn't have to be x, but I could take x to the p power should equal 3. In other words, plugging these together, 2 to the m times p over n should equal 3. So now we can start playing around with this, which you can actually start estimating this number above and below just by a little bit of guess and gosh. Let's do that just to get a handle on it, and then we can do it using the computer and figure things out. But you're trying to find and approximate this rational number so that 2 to the this equals 3. So what's the integers that you should look at? So you want the greatest integer less than or equal to this then. So try an integer that'll be too small, see if you can find one too big so that you know it's this thing plus some air. Do that arithmetic. So what is the first power you might try here? 2 to the 1. Is that too big or too small?
Small.
Okay. So what's the next one you might try? The second one you might try.
2.
What is 2 to the 2?
Too big.
Is that too big or too small?
What is the P over N?
What is the P
I
over
forgot
N?
what that was.
So I wanted 2 conditions. Condition 1 is I wanted to make sure that when I took this musical step, and when I did enough of these musical steps, I finally landed on an octave step, so that I didn't get sort of close to an octave, but not quite an octave, and end up with some dissonant chord. The second thing that we wanted to have is we wanted to have the Pythagorean ratio 3 in 3 times frequency should be a step. This Pythagorean 3 times is unfortunately called a musical fifth, which the terminology there doesn't seem to make much sense yet. I have to explain that, but we'll get to there. So I combined this equation and this equation together. So if x is 2 to the m over n, then, which is just saying that doing x in times is the same thing as doing m octaves up, which is the mathematics for this equation. Then when I plug this in here, that's raising this to the p power, which we multiply exponents, that's x to the n times p over n. Has to equal this. The important thing about this is it's just 2 to some rational number is equal to 3, and we're trying to pick this out. So the first approximation for this number, it's what's the greatest integer less than or equal to this number? So is 1 less than it?
Yes.
What about 2?
Greater.
It's greater, so does 2 work? So it has to be 1, so this is 1 point something. And so now we need to find out what that remainder is. So if we want to find out what that remainder is, this is going to be 1 plus the first remainder. And so then I'd write 2 to the 1 plus r equals 3. So how do I get rid of this 2 to the 1? Or what is 2 to the 1 plus r?
2 to the 1 times 2 to the r.
So this is 2 to the 1 times 2 to the r. So that's going to tell us that I can divide by 2 and get 2 to the r equals 3 over 2. Okay, but now when I'm trying to approximate the remainder, using the continued fraction idea, I want to get a 1 over r and approximate that. So how can I get a 1 over r in this equation? So what do I do to both sides?
The inverse. Oh, there was a, well, I guess it was 2 to the r to the negative 1 and 3 dash to the negative 1.
So what, well, if I
1
flip
over
them
2 to
both,
the
that
r.
would be putting a negative here.
Yeah.
The opposite of the rth power would be,
Positive.
You mean the rth root?
I mean the rth root.
Yeah.
So I can take the 1 over rth power here, which is the rth root on this side, and take the 1 over rth power over here. And so that's going to give me 2 equals 3 halves to the 1 over r. And when I do this, is then going to be some integer plus some remainder. Let's see if we can figure out that integer doing the same thing that we did over here. So if I'm going to do the same thing that we did over here, we're going to get a 3 halves. What's the first thing that you might guess when you're trying to squeeze 2 here?
Well, to the first would be
And the
3.
first, and so is that smaller or bigger?
Small,
3/2 is less than 2. So what's the next number we check?
2.
So 3/2
Get 9
squared
fourths,
is 9/4.
and that's big.
So now when we look at that, 9/4 is bigger than 8/4. So 3/2 squared is bigger than that. So what does that tell you about this 1 over r? So 1 over r is what's the greatest integer less than or equal to it?
9. Or did I lose track of it?
So here we said that I'm looking for 2 to some power equals 3. And so I'm going to find the integer part. Then I'm just going to repeat that. So the integer part, it's 1 plus some little bit. It's 1 point blah, blah, blah. I don't know what the blah, blah, blah is, but I can figure out the 1 because the 1 is too small and the 2 is too big. So I can just check this with integers. So now I'm doing the same thing here. I want to know what the remainder is. So I find 1 over the remainder in the expression. And this is going to be some integer, 6 point blah, blah, blah. Well, is it really 6? Well, whatever this number 1 over r is, 3/2 to the 1 over r is supposed to equal 2. So 1 is smaller than it, 2 is bigger than it. So if you're looking at 1 over r, that means 1 over r is blank point blah, blah, blah. What is the blank?
1.
It's 1 point blah, blah, blah. So that means 1 over r is 1 point blah, 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 which we might write as 1 plus 1 over r2. And so here I could have r1, and then we'll keep going, and we can keep computing these remainders like this. And so in fact, you can compute this number just using multiplication just by hand. You could express this to your students with more time if they didn't know algebra, but just knew powers. The algebra helped us speed things up. By the way, since we know algebra, if I want to call this y, if I have 2 to the y equals 3, what does y equal?
Do you want us to go back to the original expression or take the log?
Log of 3.
I like taking the log of both sides, so that's going to give me log of 2 to the y equals log of 3. So how do you
Y
think?
equals log, y log 2 equals log 3. Let's do all the steps, because I
Yeah.
don't think everybody remembers
So
that algebra.
y times
Log
log
2
2
equals
equals
log 3, and then divide both sides by log 2.
y equals log 3 divided by log 2. Sure. And so now we can do the same steps that we get here that we did with pi. Do you want me to do those steps, or do you want to do those on the calculator and save time for more music, geometry, and fun? So exercise, work out the continued fraction for log. So now exercise continued fraction decomposition. In fact, I'll tell you what you get after some step here, because it's going to get us to our piano keyboard and answer some of our questions. I think you get log of 3 divided by the log of 2 is 1 plus 1 over 1 plus 1 over 1 plus, I have it written down in fact, so maybe let me go here and just cheat, see how many ones we've got. 1, 2, and 2, 2. Plus 1 over 2 plus 1 over 2 plus, it keeps going, it's an irrational number. But this is actually a pretty good rational approximation when we look at this one. Let's actually do the arithmetic here. So what is 2 1/2? Written as a improper fraction. So that much is going to be 5 halves. Now invert the 5 halves and add 1, which write it as a improper fraction.
7.
Now invert that one
Five,
seven,
and add it to this,
12 sevenths.
and then we'll just invert it. So this gives you 1 plus 7/12 is this number here. If powers of 2, by the way, here that's because I had a 3. I could divide it by 2, which would take away 2 to the 1, and I would get a 7/12 here. It means that this number here is well approximated if you divide into 12 equal steps. If you divide 12 steps. So that means that the way you'd want to split up your musical scale here is I'd have a 1 and I'd have a 2, and then I'd have a 2 to the 1/12, 2 to the 2/12, 2 to the 3/12. Somewhere here you'll have a 2
your
to the
12 tone scale.
7/12. This is your 12-tone scale, yes. And going all the way up to 2 to the 12/12, and you can keep going. In fact, if you draw and so this is why the standard Western music is based on a 12-tone chromatic scale. This is called the equal temperament. So we've taken the Pythagorean one. Remember, this is supposed to be 3 halves. It's not 3 halves. Now when you put it on the piano, it's going to be 2 to the 7/12, which mathematically, if we want to look at these numbers, we can do a quick comparison. 3 halves is 1.5. If I do 2 to the 7 divided by 12, you get 1.4983. Pretty close to 1.5. This is making a compromise. It's getting a compromise to make the fifths and the thirds less accurate than you want, but so that the octaves in the syntonic coma will disappear. And so, can I erase this to fill in? I'm going to be able to answer questions about a fifth, and I'll play a little bit more music, and I'll look at some more patterns that we can have with some mathematics. So, keyboard has I think you've seen piano keyboards before, and they have the black keys up here that fit in between the white keys down here. This might be a middle C, D, E, F, G, A, B, C, repeats. In fact, these are the 7 tones that you got by doing the major third, minor third, major third, then up a major fifth from the root, then major third, up a major fifth, and continue doing that, which we had up in that corner. And these are the notes that are fit in between if you try to get equal temperament and get 12 equal notes. And you notice that you can get 7 steps for the 7/12 by start here at 1, 2, 3, 4, 5, 6. Well, I did that one. 1, 2, 3, 4, 5, 6, 7. This is 7/12 times the frequency. Actually, 2 to the 7/12 times the frequency of C, just C4.